Hello, Western. So today I'd like to start a new topic that we're going to continue discussing for the next few days, and that topic is waves. So the typical AP Physics definition that you'll find in most textbooks for a wave is a disturbance which travels through space and carries energy. Now, I've never been a big fan of that definition, so I've given my own definition below. I say that a wave is any physical phenomenon which satisfies the wave equation, which I've written down here at the bottom of the screen. Now, the reason I give this very precise definition for a wave is typically when you say waves, the first thing that pops into people's minds are waves at a beach. And it turns out that these types of waves are a very complicated phenomenon which isn't described very well by the wave equation. In fact, it has all of these extra terms that come on after this equation which really mess everything up. So, for example, ocean waves don't really satisfy something we'll talk about later called the superposition principle because they're described by a nonlinear equation. Another interesting phenomenon that occurs with ocean waves that won't occur with the types of waves we'll be discussing in this class is that ocean waves can break, and that's where they have these sort of shapes. And this is a very interesting thing. If you think about what's actually going on, it means that the disturbance in the wave takes on multiple values, so it's not even really a function. So, for this reason, I generally would encourage you not to think about ocean waves when we talk about waves, and instead you should think about things like disturbance along a string. A slinky is a very good example of something that has visible waves that you can see. Other examples of waves would be very shallow ripples in water or sound waves. These are all examples of waves that are pretty well described by this equation at the bottom of the screen. Now, most of the waves we're going to be studying in this class have to travel through some kind of material that we call a medium. So, for example, waves on a string travel along a string, and the string would be the medium. Other examples would be a slinky, water, sound travels through air. Now, there is one example that I want to just briefly mention that does not actually travel through a medium at all, and that is electromagnetic waves, which is just actually light. And I want to go off a little bit of a tangent here and talk about this a little bit more because it turns out this is a very, very interesting thing that electromagnetic waves don't have a medium. So if we go back to this previous equation that I had down here at the bottom of the screen, I don't really expect anybody to understand this because most of you are just starting calculus, but this value here, c, is actually the speed of the wave. And it's the speed of the wave inside the medium that the wave is traveling through. Now, the thing about this is that this number is just a constant in the equation. Now, that's a very interesting thing because if you think back to the very beginning of the year, when we were talking about Galilean relativity, we remember that velocity is relative. So, for example, if you're driving down the road, going, say, 65 miles an hour, and a car is passing you, and they're, say, moving 70 miles an hour, from your reference frame inside the car, it looks like the car next to you is just moving at 5 miles an hour. It doesn't look like they're speeding past you. From your reference frame, they look like they're just going fairly slowly. And this is called relative motion, and it's called Galilean relativity. We discussed this earlier in the year. So the question is how do we apply Galilean relativity to waves when the speed of the wave is a constant that appears in the equation? And the answer to this is that, as I mentioned before, the speed of the wave that appears in this equation is actually the speed of the wave inside the medium that the wave is traveling through. So if you move with respect to that medium, you could still have Galilean relativity. So, for example, a ripple on the surface of a water will travel at some fixed speed with respect to that water. However, you could be moving with respect to that water, and you could travel alongside the wave, and it would appear like it's at rest. Now, the interesting thing about this, though, is that I said that light does not have any medium that it can travel through, and we now see the importance of a medium in preserving Galilean relativity. So the question is how does Galilean relativity apply to light? So physicists back at the end of the 19th century, when they discovered electromagnetic waves, assumed that electromagnetic waves have to have a medium for this reason. And it turns out that in an experiment that was performed by Michelson and Morley, they discovered that light actually doesn't travel through a medium. And the result of this is that light always appears to be traveling at the same speed no matter what. So light doesn't actually obey Galilean relativity. And the importance of this is that this led to, in 1905, Einstein's theory of relativity. It turns out that Galilean relativity, the equation that seems so obvious and so intuitive, is actually wrong. So this idea that you're driving along the side of the road and if the car next to you is moving at the same speed, that car will appear at rest, is true for very low velocities, but when speeds start to approach the speed of light, the whole thing breaks down. So that's a very interesting thing. I just wanted to mention this because we don't get to talk about relativity in this class. It's not something that's part of the curriculum, and I figured this is about as close to it as we'll get. Now, getting back on track, like I said, most of the waves we're going to discuss in this class travel through some sort of medium. And what I want to think about now is what happens to the motion of a particle inside the medium when a wave travels through. So here I've got a little point on a string, and I want to see what happens to this point when the wave travels through it. So this wave is going to be moving to the right. And so what we see is that as the wave passes through this point, the point moves up. It continues to move up as the disturbance passes through it, and then after the disturbance starts to pass through the point comes back down. Eventually, the point has gone up while the disturbance passed, it comes back down, and the particle returns back to its initial position. So the important thing to understand about this is that the particle in the medium moves up and down, but it doesn't actually travel along with the wave. Okay, this doesn't happen. The particle doesn't move with the wave. So the wave, as I said in the definition at the beginning, is a disturbance. Okay, and it's the disturbance in the medium that's actually traveling. It's not the actual bulk flow of things inside the fluid. So for example, I think a lot of people, when they think about waves, they think of, like, say you've got the ocean here, and they've got this bulk thing of water, and it's like this thing of water is just moving. That's not really what's happening, okay? You have a disturbance in the water, and particles in the water move up and move down as this disturbance passes, but you don't actually have little particles in here that are all moving to the right with the wave. That's not actually what happens, okay? So what exactly is a disturbance? Well, it turns out that all mediums that waves travel through have some form of equilibrium condition. So an example of this would be, for example, gases like air. They tend to want to have a uniform density. The air wants to be kind of spread out uniformly. So when you create a disturbance, when you bunch up a whole lot of air or something like that, it creates a disturbance which will travel through the air, and that's a wave. Another example of this would be a string. When you apply tension in a string, the string wants to form a straight line. So a disturbance in the string, so for example, suppose I had a string, it wants to form a straight line, and say I pluck it and I create some kind of disturbance like this. Now, what's going to happen to this, let me change my pen color here, is that this point here at the top is going to have a force experiencing on it. So there's going to be tension in the string. It's going to apply, say, a force down like this and a force down like this. And these two forces is going to tend to bring this point back down to equilibrium. But if we think about this just a little bit more carefully, Newton says that when you apply a force, there has to be an opposite and equal force. So say some point over here, for example, is going to have a force pushing up on it, because it has to have that equal and opposite force. So as a result, at some time later, what we wind up having is a disturbance that looks like this. And so this may seem a little bit strange, and this wave, say, will be moving in this direction, this wave will be moving in this direction. But this actually is kind of what you would expect. If you think about, say, just putting a small disturbance along the surface of the water, then you get ripples that travel outwards from that center of that disturbance. And that's exactly what we have here. So we created some disturbance, and now we have these ripples that are traveling outwards. Okay? And the reason this kind of looks funny is that we're looking at a cross-section. We're just looking at one dimension instead of 3 dimensions, or 2 dimensions. So now I want to start talking about some properties that all types of waves have. So it turns out that all of the waves that we'll be discussing in this class can be broken into one of 2 categories. There are transverse waves and longitudinal waves. So all of the waves that I've shown up to this point have been transverse waves. And a transverse wave is where the disturbance is perpendicular to the direction that the wave is traveling. So, an example of that's like a wave on a string, right? Where we talked about this before. If we think about a single point on the string, it moves up and down, but the wave actually travels to the right, okay? So here the disturbance is perpendicular to the velocity. Now, there's another type of wave that we can have, and that's a longitudinal wave. And in a longitudinal wave, the disturbance is in the same direction that the wave is traveling in. So I generally like to call these compression waves, because I think that's maybe a more intuitive way to talk about them. And so the way we could create a longitudinal wave, for example, would be if you have a slinky that's stretched out, and then you suddenly compressed one end of the slinky. So in that case, you'd have this slinky here, and then you'd have this bunched up bit where you compressed it. And that bunched up bit is going to travel along the length of the slinky. And if we consider just a single point on that slinky, as this little compressed bit passes through it, it's going to travel, it's going to be displaced to the left and the right, but it's not actually going to move along with the velocity of the wave, but it'll get displaced parallel to that. Okay? So a particular point will go back and forth like this, go back and forth, but it won't actually travel with the wave. It doesn't do that. Okay? But this is an example of a longitudinal wave. So the disturbance was parallel to the velocity. Okay? Now, if we think about transverse waves, saying that the displacement is perpendicular to the direction that the wave is traveling in doesn't really tell you the direction of the displacement, because there are infinitely many ways that we could displace something and still have it perpendicular to the direction that the wave travels in. So for example, I have 2 graphs down here. Suppose the wave is traveling in this direction in both of these. So here, let's go a little bit further. Let me call this direction here vertical, and I'll call this horizontal. Okay, so here we have a wave where the displacement is in the horizontal direction. So I might call this horizontal. It's not letting me write. Polarization. Okay? So polarization is this term that we use to describe the direction of a displacement or a disturbance when the wave is a transverse wave. Because, again, there are infinitely many ways that we can have a disturbance. And so this wave here, you can see it's being displaced in the vertical direction, so I might call this vertically polarized. Okay? And it turns out that you could even have combinations of these things. You could have something like circularly polarized, where the displacement of the particles in the medium would travel around in something similar to like how a jump rope travels when it's being spun around. So I think I'd like to end the video there, and I'll start up in the next talk talking about sinusoidal waves, which is a very specific type of wave, and we'll begin discussing how we could describe the shapes of these things.